All right, welcome back, everyone. We're going to continue with that concept of sampling. So let's build on that concept. What we're going to look at now is we're going to say, well, can we now try to go backwards and say if, what can I say about the true population center? So here's an example. We've already looked at this data. This population has a population mean, so that's mu, that's the true population, of 51.379. And when I sampled, right, when I took samples, we can go ahead and observe that this is the behavior that we get. We get a sample center, so mu of x bar equal to 51.4, very close to 51.38, and a standard error of 8.885. So here's what I want to do. I want to label these. So here we have the true center of my sample distribution, mu of x bar. And for all intents and purposes, we've said that central limit theorem tells me that this equals the population center. So this value here that I observe, 51, is very, very close to the center that I observe in this graphic. Now, we know that this is a normal distribution. It looks fairly normal. And what I want to do is I want to recall that when you have a normal distribution, we have roughly 95% of the data is within 2 standard deviations of the mean, and also that 99% of the data is within 3 standard deviations of the mean, so as standard deviations. The standard deviation that I have on my graphic is 8.8. So if we're right now at 51.4, or roughly 51, yeah, 51.4, and then we go 8, we'll get very close to 60 right here. That's 1 standard deviation. And then we'll go 2 standard deviations. So that's 2 standard deviations to the right. Technically, it's sigma of x bar. And if we go 1 more, then we'll end up somewhere around here. So it would be 3 sigma of x bar. And let's go ahead and do the same thing on the left. So I'm just kind of estimating it visually, going 1, 2, and then finally 3. And we know that these little markings here would be, in other words, the standard deviations. So it would be like the z-scores. All right, here's the most important concept that actually makes a lot of sense to us. If I simply go ahead and take a look at a single sample, so a single sample is very likely to be within 2 standard deviations of the mean. Because look, check this out. If I go 2, look at all of the data points that landed within 2 standard deviations of the mean, as well as if I change it to 3 standard deviations of the mean. So a single sample has a very good chance. So maybe let me write that down, single sample. Because in reality, you're not going to take a ton of samples. You're only going to take a single sample and then try to get some information from that. So here, a single sample is very likely to be close to the true center, mu, which remember is the center x bar. So let me sketch this. We know that this is true because here I see evidence of that. If you go ahead and take a single sample from this population, so again, pretend that you don't know this right here, but if you take a single sample, then where are you more likely to land? Just looking at this graph, you're much more likely to get a sample that lands, for example, here, than to get a sample that lands over here, right? This would be unusual because we only observe a single sample that occurred here, and this is 2,000 samples. So very, very unusual to land very far away. You can also observe it here. It's very unusual for you to land way off here on the tail. It's not impossible, but it's just unusual. So again, we're taking a single sample, and I'm going to say I'm going to land here. Then what I'm going to do is I'm going to take this concept of how far did I land? Well, we have what's called the error bound. In other words, it's going to be the standard deviation. So notice here I went 1 standard deviation, 2 standard deviations. So you're going to pick how many standard deviations you want ahead of time. And then I'm going to go that distance to the right. So 1 standard deviation, 2 standard deviations. And I'm going to go 1 standard deviation, 2 standard deviations. And notice that what I get is I get this interval. So all we observe, all that we can see, because you only took a sample, is this pink right here. My center, X bar, and then I extend it to the right by 2 standard deviations. So remember that we wrote that as 2 sigma of X bar. Same thing with the left-hand side, 2 sigma of X bar. And what I want to point out is that this is something that we can actually create. And notice that we actually capture the true center. True center was right here. And this interval is able to, so from that center, we're going to add and subtract, and you're going to get something called the lower bound. So it's whatever this number is on the x-axis, and the upper bound, kind of like the fences from earlier chapter. And this idea would actually hold that if I were to tell you, oh, I'm fairly confident the true center is between these two values, then notice that I am correct. So let me try this one more time. Let's say you get another sample, again, a single sample. And let me make this in green just so that we can observe that these samples are correct. So let's say you land here. Then if I go 1 standard deviation, 2 standard deviation to the left, and then 1 standard deviation, 2 standard deviations to the right, notice that my lower bound and upper bound, if I say I'm confident that somewhere between 49 and 78, that my true center is there, then notice that I am correct. And that's because we are simply saying this statement right here, that if you take a single sample, we see that we're very likely to land very close to the center. So I'm able to create this interval. And that is what we can write out mathematically. So let me just show you one example of something that doesn't work out. We've already identified that you're very, very unlikely that if you take a single sample, that you'll get something like, for example, out here around the 80. And remember that 2 standard deviations is down this way, 1 and 2. So that length, I'm going to try to go that length here. So 1 and 2. And notice that that would be my lower bound. And if we do the same thing to the right-hand side, 1 and 2, that would be my upper bound. So notice this interval does not capture the true center at 51. This interval starts somewhere around 65 and ends maybe at 90 or 100. So this interval would be wrong. This is a bad sample. But most of the time we will get samples that are very close. So this is the concept that we can use when we're going to write out the following. So let me write out some inequalities here. And this is what we're going to be looking at now, that if you only have the sample, can you give me some information about the parameter? So our sample mean X bar is very likely to be within the error bound from the mean. And remember that when I said error bound, I meant how many standard deviations do we want to go? So the error bound is literally some number of standard deviations. And the number of standard deviations, if you guys recall, we wrote it out as Z. Z was the number of standard deviations. So it'll be Z sigma of X bar. And so what that tells me is that my sample, X bar, has to be between the true center mu, and I'm going to add, for example, 2 standard deviations. And it would be the same thing as if I went from the center minus 2 standard deviations. So let me sketch that. So what exactly does this mean? It means that ahead of time, I'm calling it, I'm saying, if I take a sample, I'm fairly confident that I'm going to be able to land within 2 standard deviations of the center, somewhere around here. Notice how this looks like a shaded region of the number of the normal distribution, which it is because you're saying all of these samples that land here in the blue are very good for me because they are what? 2 standard deviations within the center. And so if you were able to get any one of these samples, if you extend to the left and to the right, so let me visualize that. Let's say I get this sample here. Then I can extend to the right by 2 standard deviations, and I can extend to the left by 2 standard deviations. And notice that the true center X bar is in there. So mu, we can say, is this guy. And so what I said is that from mu, we go to the left 2 standard deviations, we go to the right 2 standard deviations, and my sample mean is found within that interval. So here's the sample mean. And so here we can see that that's green. And that's it. So this is a cleaner version. I'm going to leave it like this. And then what I'm going to do is I'm going to do some algebra where I'm going to say, well, I don't really want the sample mean in the middle. So let me go ahead and subtract this. So if you remember from algebra, you can go ahead and subtract from everywhere. It cancels this. And so then that leaves you with -2 sigma of X bar is less than or equal to X bar minus mu less than or equal to 2 sigma of X bar. And then what I'm going to do is I'm going to subtract by X bar through here. So do the same thing, subtract X bar. And that gives you that negative X bar minus 2 sigma of X bar is less than or equal to minus mu less than or equal to minus X bar plus 2 sigma of X bar. And then what I'm going to do is I'm going to eliminate the minus here. So multiply throughout by -1. And you got to recall that if you multiply through by -1, that the inequality signs change. So if I go ahead and do that, this distributes, so that makes it a positive X bar. So check it out, positive X bar. And then minus 2. Here I use 2, but in generally, remember, we can think of just Z times sigma of X bar. And so notice that here we have the number of standard deviations times sigma of X bar. This is from the previous section. And the minus right here goes away, so we end up with positive center mu, and similarly on the right-hand side. So this inequality that we observe here is what's called the confidence interval for the population mean. So I'm going to go ahead and say, yeah, it's technically the center of the sampling distribution, but the idea in central limit theorem is that this is the same as mu. And so therefore, we basically have an inequality that says, oh, okay, your center is within these two numbers. This number on the left is called the lower bound. The number on the right, X bar plus the number of standard deviations, is called the upper bound. So our true population mean is within the lower bound and the upper bound. X bar is called the point estimate. That's the green object, basically whatever your sample, whatever you got in your sample, that's called the point estimate. So you're just going to say that value, X bar, is fairly close to my center. And then the amount that we moved is called the margin of error, or the error bound for the mean. So here's the E, error bound for the mean. So that's the EMB. And that's Z, which, if you remember, was the number of standard deviations. And then here we have sigma of X bar. So the variability, the spread in our sample distribution. All right, that's pretty much it. All of this depends on the number of standard deviations. So before we go any further, let's go ahead and find what are called critical values. The specific values, the specific number of standard deviations that you want to move, is called the critical value. The reason for that is that it's how far you can go from the center before you aren't close enough. So let's go ahead and see an example. So let's go ahead and find the z-score corresponding to the following. Or let me make this statement first. I've already set that 95. If you go 2 standard deviations, 95% of observations are here. So we should be able to say then what percent of observations are in the tail. So in this tail and in this tail, we should have a fraction of whatever fraction is left for us to complete 100% probability. So if the blue is 95, then 5% is in the tails. And that's in both tails. So each tail has half of that. So I'll be 5% divided by 2. And 5% is 0.05. Divide that by 2, that's 0.025. So here's what we're going to go ahead and say. We're going to say, if you know the tail on the right-hand side, then this number right here, whatever z-score that is going to be represented as z and then sub 0.025. So that subscript denotes the area to the right. And by symmetry, we know that the value on the left here is minus z sub 0.025. All right, so let's go ahead and come down here. And let's just emphasize that that was the notation that we were talking about. So let me sketch that just very quickly. The z sub alpha notation represents that you have your distribution. Remember, z is your standard normal. So we're assuming mu is 0, sigma is 1. And then I'm claiming that the area to the right-hand side is alpha. So whatever number I have on my number line, that's z sub alpha. So let's quickly go ahead and take a look at this one. Let's find the z-score corresponding to this part, z sub 0.05. So remember that whenever we find something like this, you want to sketch it. Z is my standard normal, so I'm drawing my normal curve. Center is 0 and spread is 1. And now an area of 0.05 is fairly small, so I'm going to try to draw that area, shade it in, and just mark that that area is 0.05. So therefore, the number on the number line is called z sub 0.05. And I can go ahead and find whatever that number is using StatCrunch. So let's go ahead and find that number. Before I do that, let me write out the probability statement that I'll be writing. So this here corresponds to me saying, you want to land to the right of this number. So this is the probability that my random variable z is larger than whatever the heck this is. So I don't know what it is, so I'm going to put a box. But I do know that the area, the probability of that is 0.05. So let's type this into StatCrunch to get our critical value. So you can go to Stats, Calculator, Normal. Make sure that this matches. So 0 and 1, that's good. And then x has to be greater than an unknown value, but my area is 0.05. I press enter and just notice that the graphic that I see in my applet matches the graphic that I sketched. So there's agreement here. Anyway, that value is 1.645. And there we have it. We have that value. Let's go ahead and find the other two. Can you find z sub 0.1? So let's try that. Remember that we want to sketch these. Zero 0.1, that's somewhere here, area 0.1. And so this number here on my number line, this number line here, is the value such that the probability that the z, the random variable z, is greater than itself has to be equal to 0.1. So let's go ahead and find that. Use StatCrunch to find that and report out your answer. All right. Thank you for joining me. I'll see you in the next video.